the very good morning to everyone. So topic of the design analysis of algorithm is the backtracking, branch and bound and approximation algorithms. Here, this is what the introduction. In computer science, the problems are divided into classes, which is known as the complexity classes. So the complexity classes is a set of problems with related complexity. For example, when we are going to deal with some problems efficiency, or going to calculate some efficiency of an algorithm, we have to first find out the time complexity as well as the time space complexity. How fast the algorithm runs to find out the optimal solution with the minimal time and minimal cost. This is what the complexities we have to define. So the problems, with the help of the complexity theory, we have to try to cover the following: the problems that cannot be solved by the computers, the problems that can be efficiently solved by the computers, which is solved in a polynomial time, and the problems for which no efficient solution exists. It is only when an exponential time algorithm exists. So the common resources required for a solution are time as well as space. It means how much time the algorithm takes to solve a problem and the corresponding memory usage. So the time complexity is used to describe the number of steps required to solve a problem. So say space complex describes how much memory is required for the algorithm to operate or to find out the optimal solution. Here the algorithm having the time complexity of the form O of n power k. For input n and the constant value k, it's a polynomial time solution. As we discussed earlier, the computer has the capacity to solve the problems which is expressed always in terms of polynomial time. And that on the other hand, time complexity of the form k power n is the exponential time. For these cases, the solution cannot be obtained. So these are the different types of complexity classes. The first one is P class. It stands for the polynomial time. It is the collection of the decision problems that can be solved by a deterministic machine in a polynomial time. The features are: it is easy to find, it is that are solvable, and the tractable. Tractable means that can be solved in a theory as well as in a practice. So the next one is the NP class. The NP class stands for the non-deterministic polynomial time. It is the collection of the decision problems that can be solved by the non-deterministic machine. Note down, our computers are always in a deterministic manner in a polynomial time. The features of the solution of the NP class is hard to find and that are being solved by the non-deterministic machines. The problems of NP can be verified by the deterministic machine in a polynomial time. So the third one is the NP complete problems. It represents the computational problems for which no known polynomial time algorithm exists. So that exponential time complexity is required for solving the problem as the size of the input increases. It means even the moderately sized instance of this problem can become computationally intractable. So no known efficient solution can be obtained for solving the NP complete problems. The lack of efficient solution poses us significant challenges in practicing the problem solving scenarios. So it has the impact on the real world application, where it has many real world optimizations and decision making problems can be reduced to NP complete problems. The inability to solve them efficiently limits the scalability and the effectiveness of the problems in various domains, including logistic, scheduling and resource allocations. So the resource intensive due to the computational complexity, solving of NP complete problems requires the substantial computational resource including time and memory. So the approximation techniques, so it is not possible to find the exact solution of this problem by solving, so it is always use approximation algorithms to find the solution which is closer to your optimal solution. So the next topic is the backtracking. So backtrack, it is an interesting problem solving strategies that explore different options to find the best solutions. So it's like solving a puzzle by testing different pieces until we have to find the fit together perfectly. So it works by recursively exploring all the possible solutions to find to a problems. It starts by choosing initial solutions, then it explores all the possible extension of the solution. If an extension leads to the solution, the algorithm returns, or otherwise it backtracks to the previous solution and tries to a different extension. So this is all the general outline of how the backtracking algorithm works. It chooses the initial solution. It explores all the possible solution of the current solution. If an extension leads to the solution, it returns that solution. If it is not, means it backtrack to the previous and try the different extension. So the next one is the n-queen problems. It illustrates a limitation of the backtracking problems. So it explores a large portion of the search spaces, leading to the exponential time complexity. And the backtracking requires the significant memory to store and manipulate the state space. So backtracking may inefficiently explore the branches that leads to the dead ends. So these are all the important properties. Here the main application for using this is n-queen problems, which illustrates several limitations of backtracking algorithms. So the backtracking explores the largest portion of this search space, leading to the exponential time complexity and memory usage. It often requires significant memory to store and manipulate the state space. So inefficiency is ineffectively explores the branches of search tree that leads to the dead ends, especially in the cases where the constraints are not tightly enforced. For example, in the n-queen problem, placing the queens randomly or without considering the constraints may lead to an unnecessary recursive call. So solution completeness, it guarantees finding all the solution to the n-queen problems, but it takes long time. So in a practical scenarios, finding just one valid solution might be sufficient, but backtracking still exhaustively searches for all possibilities. So a difficulty in handling symmetry without the careful considerations and pruning of symmetry configurations, it may waste computational resources exploring equivalent solutions multiple times. It impact of heuristics with the backtracking can benefit from the heuristic strategies such as constraint propagation and variable ordering. Poorly choosing the heuristics may lead to the suboptimal performance or even incorrect solutions. So overall, while backtracking is a powerful technique for solving new combinatorial problems, but its limitations become apparent with the large problem size and inefficient explorations. So the next topic is the n-queen problem. It is one of the application of the backtracking. Here we have to given an n integer, place the n queens in an n cross n chessboard such that no two queens can attack each other. The queen can attack another queen if they placed in the same row or same column or on the same diagonal. Find all the possible distinct arrangements of the queens on the board that satisfy this condition. The output should be an array of solution where each solution is represented as an array of integers of size n, and the ith integer denotes the column position of the queen in the ith row. If no solution exists, returns an empty array. The main idea behind is using the backtrack to place n queens on n cross n chessboard. We proceed either row by row or column by column. This is a constraint for each row. Try to place a queen in every column and check if it is safe. That is, no other queen in the same column or row or the diagonal. If safe, place the queen and move to the next row or the column. If no valid position exists, backtrack to the previous step and find a different position. Continue until all the queens are placed or all possibilities are explored.